Today we're going to talk about the average value of a function. So given any function, it's going to do whatever it's doing. But if we wanted to figure out, okay, what is the average of the function over a specific interval? So if we wanted to sum this up and say, okay, on average, we're right there. How do we do it? Now, basically what we're doing is we're trying to convert our function that's doing all this wavy stuff and having these peaks and valleys and whatever else into a rectangle. So if we could chop off all of these and then fill in all of our gaps here, how level and flat. So that's what we're looking at with our average value. And it's the type of thing you would get with an average elevation of a city or of a state or of a country or of a town, whatever. Taking all of the different elevations, and if we leveled everything out flat, what would that elevation be? So now a way we can do this is say we would take all of these specific y values. Y would be our y sub 1 plus our y sub 2 plus, and we would add these all up to our y sub n, however many we have, divide by n. Normal average. Add things up, divide by the number of things you got. Thing is, though, when we do this finite number, we're missing a whole lot. That the value we pick here is not necessarily representative of everything around it. So another way we can do this is kind of what we did with our Riemann sums, is we will get a representative over a specific region. So say we want to do our, we could do our right hand notation, we could do our left hand, we could do our midpoint, however we want to do it. But we don't want to just divide by an n, because that doesn't necessarily represent the whole thing that's going, because each of these is taking up a bit of a distance. But now if we divide these into equal partitions, if we're going from some a value minus a, that distance would be the distance of each gap times the number of gaps. So we can do this b minus a divided by delta x would equal our n value. So now we have another way to quantify this. So if we do that substitution, we get this y1 plus y2 plus, and we add these all up to our y sub n, and that's divided by b minus a over delta x. Now dividing fractions, we can then change this and multiply by there. Now, of course, this is just an estimate, and then even back here, I should probably not have had said equal to. We should have said approximately. And so a way that we could rewrite this would be, oh, even let's start this over. 1 over b minus a summation of I equals 1 to n. And instead of calling it y sub 1, we could call it f of x sub I. And here we're just going to say delta x is a consistent length, so we don't have to worry about the i's. And now you can probably see where this is going. This is a very familiar setup. In order to get an exact value, we would take the limit as n goes to infinity of this summation and what's going to turn as an integral. Nice one. We often call this F, and then we'll abbreviate it with AVE underneath. And sometimes they'll put it of X, sometimes they'll drop that. But it's that F with a little average underneath written. But here's our equation. And if you think about it, it's what we're trying to do with an average. Add things up, divide by the number of things. An integral is essentially a big summation, and then we're kind of dividing by how far are we doing it over, or quote unquote, the number of things that we're adding up, if you want to think of it along those lines. So let's do some examples. We want to do the average value of f of x equals 1 plus x squared on the interval of -1 up to 2. Now, it's very important that you have an actual interval for all of these average value problems, because without it, we can't compute this. We need to know what our interval is going to be. So going -1 up to 2, 1 plus x squared, and then our dx. Fairly basic. Oops, sorry. Almost forgot. 1 over 2 minus a -1. So 1 over 2 plus 1, so it's a, and then we do our integral. One third, we get 3. Whoops, got 3. It's 2 plus 8/3 minus -1 minus 1/3. So minus a negative becomes a positive. And so we have that 1/3. And then adding our whole numbers, we get 3. And our fractions, we get 9/3, which is another 3. So we get 6 times a third. So it's 2 units long, whatever our units are that we're using to measure this. Next thing, related to this, is we want to look at the mean value theorem. Now you've done this before. Why are we doing it again? This is the mean value theorem for integrals. So this states that if f is continuous, on some interval a to b, then there exists, this backwards e means there exists, some number c that is in this interval, so or on this interval, so it's between somewhere on that a to b, such that f of c is going to equal this f average, which is 1 over b minus a, integral from a to b, f of x dx. Or if you want to write it a different way, b minus a times f of c is going to equal this integral But now let's think of this. Here's what we're doing. Why does this theorem make sense? So here's our function. It does whatever it's doing. And we find its average value. Now, important thing here is that this function is continuous. There's got to be at least one spot where it fills in that average. So since it's continuous, we're going to draw this without picking up our pencil. And so whenever we take these valleys or these hills and we chop them off to fill in these valleys, since we're looking for the average value, we know that we're going to have some parts above it, some parts below it. So in order to get an average, there's got to be at least some spot that is equivalent to whatever that average height is going to be. Now, in this case, there are 4 spots that are going to work for that. But depending on what the function looks like and a few other things, there's at least one. So that's what we're saying. That when we have this, if we're going to level out our uneven terrain, there's going to be at least one spot that's not going to need to be modified. So let's go ahead and take our example and let's apply the mean value theorem. So our function is 1 plus x squared. We're on the interval of -1 up to 2. Let's find that c value that this is going to work for. So average value, so our f of c is going to equal 1 over 2 minus a -1, integral from -1 up to 2 of 1 plus x squared dx. We found out that our answer was a very nice 2. All right, so f of c equals 2. Now, f of c, when we're doing this, it's going to be a 1 plus c squared equals 2. So c squared equals 1. So c is going to equal a plus or minus 1. So both spots on this interval, since -1 to 2 includes both -1 and 2, both of them are going to work. So just to take a look at what this is going to show us, there's -1, there's 2, there's 2. Our graph here looks something like this. And this is actually way up here at 5. So 3, 4, 5, where that point is. But if we draw this line at 2, we see that it's hitting our graph at -1 and at +1. And there's our average value. Took this whole thing, this extra bit up here would fit level everything out. So 2 basic equations. Well, one basic equation we have to worry about is that this is going to be our average value function. It's just an integral going from an a to b, but then we compensate by dividing by that distance. That gives us our average. When we're talking about mean value theorem, as long as our f is continuous, there's going to be at least one spot where we can plug in a value into our initial function that's going to equal this average.